Hello, my dear students. Welcome back to the online lecture video series on electromagnetic theory by AVS Deepak. In the previous module, we have seen the basics of vector algebra and the concepts of three-dimensional coordinate geometry. From this module, we would apply those basics on the problems of electromagnetics. We start the discussion of electromagnetics by electrostatics. Electrostatics is the study of charges at rest. Even when charges are kept at rest, they would have an effect around them. What is the nature of effect due to various types of charges at rest is what we will be seeing in this module. To do that, let us look in the concepts which you might have seen earlier in your earlier classes. You know that by nature, force between two like charges is repulsive. But how can this force be quantified? Let us look at the following scenarios and try to understand the quantification of electric force. Consider two charges Q1 and Q2 both being positive charges, hence the name like charges, separated by distance of 4 units. As I have told you, the direction of the force is pulling these two charges away from the center. This would also be this way and this would also be. So the direction of the electric force would be in the given manner. And let the thickness of these lines represents the strength of the repulsive force. Let us now discuss these same charges but at reduced distance. That is, these charges are brought closer. What would happen to the repulsive force? The force is still repulsive, mind it, but the magnitude has increased. You may observe by the thickness. So, if charges are brought closer, then the repulsive force between them is more. Similarly, if charges are made further, then the repulsive force strength would decrease. What if instead of like charges, we have unlike charges? Force between unlike charges is attractive. Now, this attractive force pulls these both charges towards the center. Let this thickness again represent the strength of attractive force. Now, if these charges are put at larger distances, that is, if the separation between these charges is increased, still there would be an attractive force, but not as strong as the earlier. What if the distance is made smaller? That means there will be very strong attractive force between them. So these are quantified. So these values of forces have been quantified by Coulomb. He has identified that the electric force between two charges is directly proportional to the product of the magnitudes. And not just that, it is inversely proportional to the distance of the separation between them, where R stands for the distance of separation. Thereby, the name inverse square law. This inverse square law, you might remember, is not just applicable for the electric force, but there are many forces which follow this inverse square law. Now, the direction of the force is AR cap, where AR cap is along the line joining those. So, the expression of the force between two charges Q1 and Q2 in free space is given by 1 by 4 pi epsilon naught Q1 Q2 by R square AR cap, where this 1 by 4 pi epsilon naught is the proportional constant. You may see that here, see, these are both proportional symbols. So to make it an equal symbol, we need a proportionality constant K. This 1 by 4 pi epsilon is one such proportionality constant. Epsilon naught is called as permittivity of free space. What is this permittivity? We'll discuss in the subsequent section. Consider the following setup, where there are three charges, charge Q1, charge minus Q1 and charge minus Q. You are asked to determine the direction of the force experienced by the test charge minus Q. This is the test charge. What is the force? What is the direction of the force experienced by this? Now, how to solve this problem? To solve this problem, let us use the principle of superposition. The principle of superposition says that if there are more than one sources acting on a body, then the net resultant is just the algebraic sum of the resultant because of individual sources. So due to that, let us consider the force experienced by the test charge minus Q because of minus Q1. See, these minus Q and minus Q1 are both negative charges. Hence, the nature of force is repulsive. So, the direction of the force would be directed away from the center. Now, similarly, what is the force experienced by the test charge minus Q because of plus Q1? Remember that these are unlike charges and these unlike charges attract. So, the resultant force because of plus Q1 is in this direction. Now, we have two forces here and there. So, what is the resultant force? The resultant force is along this direction. How did we get there? Let us again consider the principle of superposition, that there are two forces acting on a body simultaneously, then the net force is the sum of the individual forces when the others are nullified. So now for the scenario, first scenario, let us nullify this force. Let us consider only F1. So a body which is here would be directed in this direction. This is the initial point. Now, once you are here, let us nullify F1 and let us consider F2 only. F2 takes the body in this direction. So, this is where the final point. Now, the resultant is from initial point to final point. This is the resultant. This you might have seen as parallelogram law. Parallelogram law says if there are two forces acting on a body simultaneously, then the net resultant force is along the parallelogram formed by the two vectors. So imagine that this is the parallelogram, this is the resultant diagonal, that is same as what we got using the principle of superposition. Now, we have used the principles of superposition to determine the net effective force on the test charge minus Q. As the electric force follows the principles of vector addition, parallelogram law can also be applied. This principle of superposition can be used to solve much more complex problems in electrostatics. We will discuss one of them here and the others in the subsequent modules. Before we do that, let us discuss about a physical quantity called electric field intensity. If you remember the expression for force, force is given by 1 by 4 pi epsilon naught Q1 Q2 by R square along the direction of AR cap. Now, imagine that you have a source charge. You have a charge which is at rest. As I told you, that the electrostatics is study of charges at rest. Now, imagine that you have a good charge, good amount of charge at the source. So, your Q1 is your Qs. Now, what you want to discuss is, if there is charge, what is the effect of this charge? What would this charge do? Is the question you are wanting to answer. But as you know, we don't have any physical quantity which says that. But we have an interactive physical quantity called electric force. This electric force requires two charges. So let me call the second charge Q2 be QD. So the electric force is dependent not just on the source but also at the destination. But I want to define a physical quantity which is not dependent on the destination. I want to study the effect of force. Such physical quantity is electric field intensity. Electric field intensity is defined as the force experienced by unit positive charge. That is, the destination charge is plus 1. Hence, the force experienced by unit positive charge is 1 by 4 pi epsilon naught Qs by R square AR cap. This R represents the distance from the source and AR cap represents the positional vector of the destination point, considering that R plus Q is at our origin 0, 0. Right? Let us understand what more shall this electric field intensity has to offer. Now it is denoted by E. So the force per unit electric charge is denoted by E bar. Now the relation between E bar and F bar can be quantified as, see, I have defined this electric field intensity to be the force per unit positive charge. But what if I cannot get a unit positive charge in my hand? but I have a standard quality of charge, standard quantity of charge QT. Then my F bar would be 1 by 4 pi epsilon naught Qs Qt test charge by R square AR cap. But I don't want the force per Qt charge. I want to have the force per unit positive charge. Hence, Qt would give me, or conversely, I can also say that if you already have electric field intensity, you want to determine the electric force for some random charge QR, then I don't have to apply inverse square law again. I can also say that my force is directly E bar times QR. So the relation between the electric field intensity and electric force is both these expressions. They are the same expression written in a different form. So E bar equals to F by Q, or F bar equals to Q times E bar. Both of them stand for the relation between E bar and F bar. Remember that this is not a dot product, it is just a multiplication sign. Now, let us try to determine the electric field intensity due to a point charge. Electric field intensity because of charge Q in free space can be given by this expression which I have just obtained, where Q is nothing but Qs. You may go a bit back and you might already see that I have obtained this E bar to be F force acting per unit positive charge, where I made Q2 equals to 1 and Q1 equals to Qs, in this case Q. So this is the electric field intensity distribution because of charge Q in free space. Remember, where air cap is the unit vector along positional vector, where the charge Q is assumed to be placed at the origin and the positional vector is any vector joining the origin to the. Hope this is clear. Now let us discuss. See, this is I'm just showing this in an animation. The source is assumed to be at origin, and the test point is at P. Then R bar is nothing but the positional vector. So AR cap would be the unit vector along the positional vector. Now, please, by using the principles of vector algebra, I can write that AR cap is nothing but R bar by mod R, that is R. So I can also say E bar to be equals to 1 by 4 pi epsilon naught Q by R cube in the direction of R bar. This is also a valid expression. Now, let us discuss the electric field intensity due to distributed system of charges. That is, in the earlier scenario, we had only the electric field intensity because of a single charge. What if instead of one charge, we have n distributed charges? Again, using the principles of superposition theorem, the net electric field intensity can be equal to the sum of individual electric field intensities, where all others are nullified while discussing one. That is, when E1 bar is being determined, all other sources, all other charges are kept 0. Similarly, when E2 bar is being determined, all other charges are kept assumed to be 0, and we determine the electric field intensities and we add them. This is just an application of superposition theorem. Now, electric field intensity because of charge 1 is 1 by 4 pi epsilon naught q1 by r1 square along ar1 cap, where ar1 is unit vector along the line joining the first charge to the given point. Similarly, I can also say En bar to be 1 by 4 pi epsilon Qn by Rn square Arn cap, where Arn cap is the unit vector along the line joining the nth charge to the given point. Let me show you in this diagram. Q1 is here, Q2 is here, Qn is somewhere here, right? You can also assume any points, Q3 being here, Q4 being here, Q5 being here, what not. Now this is the test point. So this is R1 bar, this is R2 bar. R1 bar is the line joining the first charge to the test point. R2 bar is the line joining second charge to the test point. Rn bar is the line joining the nth charge to the test point. Similarly, I may have R3 bar, R4 bar, R5 bar, and so on. So the net electric field intensity would be acting along this E1 bar, E2 bar, plus E3 bar, and so on. The sum, algebraic sum, would give me the final electric field intensity. But instead of discrete charges, what if we have continuous charges? See, in the previous problems, I had discussed, in the first scenario, there was only one charge in the entire free space. Now we have discussed the electric field intensity because of it is being radially outward. Right? I hope you understand why I meant radially outward, because of AR cap, right? Now in the second scenario, I had multiple sources, 1, 2, 3, 4, 5, 6. These are all distributed. Now in the current scenario, my sources are not distributed, instead they are continuous. What I meant by continuous is, for example, imagine your screen. The entire screen is filled with charges. Imagine a cup. Entire cup is filled with charges. This type of distribution of charges is called continuous charge distribution, whereas these are called distributed charges. Sometimes they are also called discrete charges. To do discrete charges, we have already seen that net effect E equals to summation of n equals to 1 to n En. But that cannot be applied for continuous charges, because continuous charges cannot be separated as we could do in the case of distributed charges or discrete charges. So how to determine the electric field intensity because of the continuous charges is what we would see in the current model. You may see in the earlier scenario, I have said that the charge can be your screen. Your screen, you may see, is a two-dimensional entity. Your screen is a two-dimensional entity. Now, in another case, I have told you that it may be inside a cup or cooler, right? You guys like drinking this tea in cooler, right? So this can be colored. Now, if it is colored, it is a three-dimensional entity. Or it can be along a line. A line is a one-dimensional entity. Now, your charge distribution can be one-dimensional, two-dimensional, or three-dimensional. When to consider one-dimensional charge distribution, two-dimensional charge distribution, and three-dimensional charge distribution? What if these charges are distributed in such a way? How to determine the electric field intensity because of this distribution is what we are interested in finding. In the current module, we would only discuss about the one-dimensional charges, that is the wires. We will not discuss the second two-dimensional body in the current module, although we will discuss that in the next module. The three-dimensional module is discussed much later while we discuss the Gauss law. What these are, you don't worry as of now, but let us move further. Now, the problem is varying, the problem statement itself varies with the geometry of the source. Now, electric field intensity due to a line charge. A line is a one-dimensional entity. See the question. First, see the question. Consider a charge distributed uniformly along a straight line of length L with the charge density rho L. You may see in the question it has been given that uniform charge distribution. The difference between uniform charge distribution and non-uniform charge distribution is, for example, consider this wire, right? Assume this to be a straight line like this. This is looking more like straight line. Ignore this. Now, consider this straight line. If you consider any quantity here, scenario A, scenario B, and C, where equal lengths of dl are considered. Now, the charge in scenario 1 would be equals to rho LDL. Charge at scenario 2 should also be equals to rho LDL. It would also be equals to rho LDL. If that is the case, then this distribution is called uniform charge distribution. If not, if QA is not equals to QB, if it is not equals to QC, then this is called non-uniform charge distribution. Where I should also tell you rho L is called linear charge density. The meaning of linear charge density is charge situated in a line of length 1, or I can also say unit length. The technical definition would become linear charge density is nothing but charge per unit length. Now, if this is constant over all the length of the wire, then it is called uniform charge distribution, otherwise non-uniform. Now, in our scenario, we discuss the uniform distributed wire. Now, I want to determine the electric field intensity because of such charge. Now, sir, let me tell you another important aspect of these dimensions. you are talking in optical fiber scenario, right? What is an optical fiber? Optical fiber would be looking like just a line of any sort, right? Just a line of any sort, right? Here, this would be a three-dimensional quantity. The same wire, when we are discussing electricity, this would be a one-dimensional quantity. In fact, it might quite possible that the cross-sectional area of this optical fiber is much less than the cross-sectional area of this wire. I am not saying that it is possible, it is the only case, but it is possible that the cross-sectional area of the optical fiber is less than the cross-sectional area of the wire. Still, the optical fiber would be considered three-dimensional, whereas wire would be considered one-dimensional. Why so? The reason being, for a wire, the cross-sectional area would not be comparable to the other aspects, other physical dimensions or other physical measures we may have the problem. For example, distance from the wire. Distance from the wire might be much larger than the cross-sectional area of the wire. Hence, the cross-sectional area of the wire would be neglected and it is considered only to be a one-dimensional body. Now, if you can limit this one-dimensional body to smaller lengths, negligible lengths, now it is quite possible that this length itself is also negligible compared to the distance from this wire. In that scenario, we may even consider a no dimensional entity, and no dimensional entity is nothing but why am I discussing the same type thing? Because if we have a point charge, we can know the electric field intensity. If we don't have a point charge, we don't have any electric field intensity. We don't have any other means. So what I'm doing is I am limiting my wire to a point. That is, I am determining the electric field intensity due to a point charge of this one. Similarly, I can also determine the electric field intensity because of this point, this point, this point, this point, and so on. But the difference between the distributed charges and continuous charges is now I cannot add them up because it is physically not possible to separate a continuous charge distribution. So what I would do is I would use integration instead of summation. That is the fundamental change between a discrete entities and a continuous entity. To determine the net effect because of discrete entities, the summation I will be using is the sum. Whereas to identify the net effect because of continuous entities, the summation I would be using is this understanding is much more critical than you think, because it has been it might be feeded to us that if it is discrete, we'd be using sum. If it is continuous, we'd be using integrations. Why so? This is the reason. Because it is not possible for us to separate a continuous charge distribution physically. If we can do physical separation, however close they are, we can still use the summation. But because they are not physically separable, their sum net effect cannot be added using summation. We would be using integration. I hope the reason why we would be using integration is clear. From this, we will move to solve the problem of electric field intensity because of a line of length L where the charges are distributed uniformly with distribution rho L. This is the construction of a problem where the entire charge can be written as integral of rho L dl, where the small possible charge is rho L dl, where dl is the smallest possible length. Now the electric field intensity is the integration of electric field intensities because of the smallest possible charges dq. Now you know that the electric field intensity because of smallest possible charge dq would be dq by 4 pi epsilon naught r square. When I integrate that, it would turn to integral of rho L dl 4 pi epsilon naught r square ar cap. Although this expression is looking easy, you might be getting a feel that you have solved the problem. Let me tell you, we have just constructed a problem. We are nowhere near to solving it. Because from now, I should be determining all the values of AR cap and the values of R square and then integrating them. This is the real problem here. Because rho L is a constant, 4 pi epsilon is a constant. This dl, remember you, is differential length element, which we might have discussed in the earlier. Right? So let us look at the geometry of the problem. Again, this AR by R square can be equated to R bar by R cube. So to solve the problem, let us consider that the line is aligned along Z axis. So if it is aligned along Z axis, then dl is dh. Why dh? Because we solve this using cylindrical coordinate system. Why cylindrical? We would see. So these are the directions x, y and z. This is placed at along z1 and z2. This is a point x, y, z. This is the test point. This is the test point. Right? Now, my intention is to determine the electric field intensity here at some point x, y, z because of this charge. Now, let me tell you z2 minus z1 equals to L, because L is the length of the wire. Okay. Now, consider the smallest possible region on this. Now see, the smallest possible region its dimensions are negligible compared to this distance, hence this can be considered a point. Let this point be equal to 0, 0 and now if this change, z dash would change. So change in this point would mean change in z dash. I use this z prime. I use this z prime to differentiate this point from this point. That is, the value of z at this point and the value of z at this point are different. Hence the notation z prime. Now this dz prime is the smallest possible length. The smallest possible length, I can be considering it as a point. Now I have drawn a line which is joining that to this. You may see using the principles of AB bar equals to x2 minus x1 ax cap plus y2 minus y1 ay cap plus z2 minus z1 az cap. The line joining 0 comma 0 comma z dash to xyz can be written as xax plus yay plus z minus z dash az cap. So the expression for electric field intensity can be written as this. The limits of the integration are from z1 to z2, rho L by dz. The magnitude of this is r. So r equals to x square plus y square plus z minus z prime whole square to the power of 1 by 2. This is r. So r cube is this raised to the power of 3 by 2. So you may not be seeing that clearly, so let me write it here. R can be written as x square plus y square plus z minus z prime to the power of 1 by 2. 1 by 2. So r cube would be this entire thing raised to the power of 3 by 2. But see, this integration is not an easy expression to solve. I am not happy with this expression. It is not looking easy to solve at all. So I don't want this expression. That is why I would not solve this problem in Cartesian coordinate system. We would solve this problem in cylindrical coordinate system. The reason why I said cylindrical coordinate system, it would be clear to you when I discuss the vector joining this point to this point. Observe how I got from there to there. First of all, I'd be traveling along a direction perpendicular to h. Direction perpendicular to h would be rho. Now, from there, I would be moving along h to reach here. I have travelled a magnitude of rho along the direction of a rho cap, and I have travelled along h minus h prime along ah cap. So this is my vector. See this? Rho arrow cap plus h minus h prime ah cap. This is my vector, where because you may identify that I have represented this point being h prime. Yes, if you are thinking you are correct, h prime is nothing but z prime, h1 is nothing but z1, h2 is nothing but z2, because h is nothing but z in the relation between Cartesian coordinate system and cylindrical coordinate system. But see, earlier there were 3 unit vectors. Now the unit vectors were limited to 2. Observe, that the vector did not change at all. The vector is still the same. Only change was now I have fewer less variables to worry about. Right? Now let us see what happens. Let us look that the angle between this vector joining the given point to the test point and arrow cap. This is nothing but arrow cap, right? This is nothing but arrow cap because I told you when this is rho arrow cap, this is also rho arrow cap. So the angle between arrow cap and this is alpha. Let that be alpha. Again, this would be alpha. That is alpha, this is alpha because they are interior alternate angles. So now if you see that I have formed a beautiful triangle over here. This h minus h prime, alpha, rho, and r formed a beautiful right angle triangle. From trigonometry, I can say that sin alpha is h minus h prime by r. Sin alpha would be h minus h prime by r. Cos alpha would be rho by r. So tan alpha would be h minus h prime by rho. So I can also say h prime is h minus rho tan alpha. Why am I doing all this? What I'm doing is instead of these h's, I'm trying to migrate this expression into the alphas. What are we getting out of it? You'll see. Right? Again, from this expression, that rho r by rho is nothing but secant alpha. So r equals to rho secant alpha. I need not go to this entire thing. I can also directly write this over. Right? But the end result is r equals to rho secant alpha. Remember that this is the expression we are trying to solve, where this is my rho r cube, this is my r bar, right? So this expression is nothing alien. This is the same expression. It is just that we have expressed this in terms of rho and h. Right. Let us determine the angle. Let us assume that the angle, the vector joining h1 to the test point is making alpha 1 with rho. Similarly, the vector joining h2 to the test point is making alpha 2 with arrow cap. Again, you may understand that this is not making an angle there. This is making an angle here, but this angle and those angles both are similar, same because they are interior and alternate angles. Now I know that h prime is h minus rho tan alpha. Now I can also write that h1 is h minus rho tan alpha 1. Because for all these points, rho is same. Because rho is the perpendicular distance from h-axis to the point. So that is constant. Alpha 1s are the change. Similarly, h2 would be h minus rho tan alpha 2. Now, as I told you, my interest is to transform this into much more simpler problem. Now, I have already shown you that this entire nonsense can be written as rho secant alpha to the power of 3. because this is nothing but R cube, where R equals to rho secant alpha. So this entire nonsense I can write to be rho secant alpha cube. Right? Rho L is still the same. So instead of integrating from H1 to H2, I'd be integrating from alpha 1 to alpha 2. But what is the differential element? dH prime, where H prime was equals to H minus rho n alpha. So dH prime would be dH, that is not changing anywhere from the point, minus d rho tan alpha minus rho d tan alpha. Again, rho is not changing as long as the point is not changing. So dH prime is minus rho secant square alpha d alpha. Right? Similarly, rho is rho, H minus H prime can be written as rho tan alpha. So you may find my writings difficult to follow, but I can show that in print, right? So this is what I have written you. I hope if you want to know how did I get there, you may go to my previous the instant of the video, or even you may solve it on your own from the expression that h prime equals to h minus tan alpha times pi. So see, that is what I have done here. I have taken the minus sign outside. This entire thing r square has been written to rho. This is also again an unnecessary time waste. I would have directly written it as rho cube secant cube alpha if you could follow, or if you could not, this entire thing I have written as rho square secant square alpha times that is a reason to the power of 3 by 2, that would give me rho cube secant cube alpha. Again, rho is rho, h minus h prime is rho tan alpha. Right? Now, if by solving this expression, I can cancel them out. Right? The secant cube, then secant square would be cancelling, remaining secant, and this rho and rho would be cancelling out, right? Rho square again, this can be cancelling it here, so I'd be getting with remaining with rho secant alpha here. So I'd be getting the secant alpha. If I take the secant alpha here, it would be cos alpha, and tan alpha by secant alpha would be sin alpha. So this is my final expression which is to be integrated. Look how small this integration is looking like. Integration of cos alpha, wow, minus sin alpha, integration of sin alpha, cos alpha, right? Oh my god, right? So how small it looked, how big the expression was before we started, and how small it is looking. This is why we have used cylindrical coordinate system instead of Cartesian coordinate system. That is why we should always be ready to change one coordinate system to another coordinate system. That is why we have discussed conversion of vectors in one coordinate system to another coordinate system. But that aside, let us come to the problem right now. Still, because we still have to integrate, integration of cos alpha would be minus sin alpha, or sorry, sin alpha, integration of sin alpha would be minus cos alpha. So I am here still. So this is integration of cos alpha sin alpha minus integration of sin alpha is cos alpha. That is minus cos alpha. So when I substitute the limits, I will be lefting out with sin alpha 2 minus sin alpha 1. There is a minus over here. Sin alpha 1 minus sin alpha 2 times a rho plus cos alpha 2 minus cos alpha 1 times a h cap. So this is the final expression for electric field intensity due to a finite line charge. What is alpha 1? Alpha 1 is the angle. You may remember H1 is making with rho, alpha 2 is the angle H2 is making with. So just if you have the angles it is making, then you will be able to solve this problem. This expression is the final expression for electric field intensity because of a finite line charge. But you may be worried that what the hell is this expression? Right? Where the hell would I have the line charge along z-axis? And how the hell am I supposed to determine the aero cap? And even if I do that, how the hell am I going to measure the angle it is making with the aero cap? So don't you worry about them, because physically speaking, if you have a line, for example, in this direction, clearly it is not AZ cap or AH cap. Now, what you mean by aero cap is a vector which is perpendicular to this. What I mean by AH cap is a vector in this direction, in the direction of the line charge. Now, once you know this, you can obviously determine, if for example, if the line is from here to here, you can obviously determine this angle. Even if you can't determine this angle, this is nothing but 90 minus this angle. Similarly, look at this. You have to know this angle, but even if you don't know that, you have to determine this angle, 90 minus theta. Now, if you assume that to be 90 minus theta 1 and 90 minus theta 2, right? So, you'd be getting, these are alpha, right? We have used the representation of alpha 1 and alpha 2. For example, if this angle measures at 30, that means your alpha 1 would be 60. Right? I hope this, by this you'll understand what I mean by coordinate geometry. Coordinate geometry is not written in stone, right? It would be molding to our requirements. Right? It is the expression of electric field intensity of a line charge, where aero cap is the direction perpendicular to the test point from the line charge, right? And AH cap is the direction of the line charge. And alpha 1 and alpha 2 are the angles between the perpendiculars to the end points. Or otherwise, as I have already mentioned, that you may just measure them with the line, but we have to then subtract that angle from 90 to get at alpha 1 and alpha 2. So this is your assignment. We have considered a line to be of finite length, but what if the line is of infinite length? What would be the electric field intensity in such scenario? You please determine that and submit it in your Google Classroom. Thank you. You may follow, sorry that I am missing my reference page, you may follow StudyCo again to refer this concept.